Friends, good morning to all of you. Myself, Professor P. Venugopal, working as an assistant professor in Electronics and Communication Department from Sri Sai Ram College of Engineering, Hanekal, Bengaluru. So today, in this session, I am going to deliver a presentation on the topics in the optical sources. In this lecture, we'll learn the following topics. One is energy band. Next one is the direct and indirect band gaps. Third one is the light emitting diodes, LED structures and light source materials. Energy bands. Dear students, you are all aware of the matter, three states of matter: solids, liquids and the gases. Arrangement of molecules in the solids, as you know, is very closed. Arrangement of molecules in the liquids is the moderate, but arrangement of the molecules in the gaseous state is very loosely packed. The electrons in the atoms of the molecules tend to move into orbitals of the neighboring atoms. Hence, electron orbitals overlap when atoms comes together. In case of the solid state, the molecules are very tightly packed. The electron orbitals overlap. So, when the atoms comes together, due to this intermixing of atoms in solids, instead of single energy levels, there will be bands of energy levels formed. This set of energy levels which are closely packed are called energy bands. See, in this you are observing two types of bands: valence band, conduction band. In between valence band and the conduction band is the forbidden energy gap or the energy band. Next thing is valence band. So as I told you, we have the bands, energy bands. One is valence band, one is the conduction band. In between valence band and conduction band, we have the band called the energy gap or forbidden energy band. Let us understand what is valence band. The electrons moves in the atoms in certain energy levels, but the energy of the electrons in the innermost shell is higher than the outermost shell electrons. Dear students, in valence band, energy of the electrons in the innermost shell is higher than the outermost shell electrons. The electrons that are present in the outermost shell are called valence electrons. You already studied the carbon is in tetravalent electrons, tetravalent atom or the element, because there are 4 valence electrons around the carbon atom. Therefore, we call carbon as a tetravalent element. These valence electrons containing series of energy levels form an energy band which is called as valence band. The valence band is having the highest occupied energy. Next is conduction band. The valence electrons are so loosely attached to the nucleus that even at room temperature, few of the valence electrons leave the band to be free. These are called as free electrons, as tend to move towards the neighboring atoms. These free electrons are the ones which conduct the current in a conductor, and hence they are called conduction electrons. So conduction electrons means they are the free electrons which conduct the current in the conductor. The band which contains conduction electrons is called the conduction band. The conduction band is the band having lowest occupied energy. And you observed in the valence band. In the valence band is the band having the highest occupied energy. Next thing is the forbidden gap. So gap between the valence band and the conduction band is called as the forbidden energy gap. As the name says, this band is the forbidden one without energy. Hence, no electron stays in the band. So, no electron stays in the forbidden energy gap. The valence electrons, while going to the conduction band, pass through this. So, electrons are flowing from valence band to the conduction band, so which is going through this forbidden gap or the forbidden energy band. The forbidden energy gap, if greater, means the valence band electrons are tightly bound to the nucleus. In order to push the electrons out of the valence band, some external energy is required, which would be equal to forbidden energy gap. Look, dear students, so if you want to move the electrons from valence band to the conduction band, first the electrons are tightly bound to the nucleus. So in order to push those electrons out of the valence band, so we need some external energy. That external energy is equal to the forbidden energy gap. So next topic is that direct and indirect band gaps. So this is a circuit diagram. The first one is the direct band gap, and second one is the indirect band gap. So this is the waveform for this waveform for direct and indirect band gaps. So here direct band gap material. So which is the direct band gap material? Then what is a direct band gap? Various dopants are added to p-n junction of the gallium arsenide to get emission over a wide range of colors. Gallium arsenide is preferred over semiconductors like silicon and germanium. Silicon and germanium are what you call it as the tetravalent impurities. Therefore, gallium arsenide preferred over semiconductors like silicon and germanium, as gallium arsenide is a direct band gap material. So gallium arsenide are observing here as a direct band gap material. In a direct band gap material, the bottom of the conduction band. So refer to the figure, you understood very much better that in the direct band gap material, the bottom of the conduction band lies directly above the top of the valence band. So in the first figure, okay, the first one is the what you call it as the conduction band, and below one is the valence band. So in the direct band gap material, the bottom of the conduction band lies directly above the top of the valence band. Here K is equal to 0, the energy of electrons in the conduction band, with 0 of energy being at the top of the valence band. So this is given by energy of electrons in the conduction band is given by En is equal to delta. Delta is the separation of the conduction band and the valence band. Delta plus Pn square by 2m, which is nothing but delta plus h square k square divided by 2mn square, where k is the constant, which is 2 pi by lambda, is the wave vector, where lambda is the wavelength. Energy of the holes in the valence band is given by Ep is equal to h square k square by 2 mh. So next type is the indirect band gap. Semiconductors like germanium and silicon are indirect band gap material. In this band gap material, bottom of the conduction band is shifted from k is equal to 0 to k is equal to k naught, so that energy is given by En is equal to delta plus h square into k minus k naught whole square by 2mn. See, photon transition from the conduction band to the valence band in the indirect band gap is horizontal in nature. Dear students, this photon transition from conduction band to valence band in the direct band gap is vertical in nature. That you can observe in the waveform of this direct and indirect band gaps. And the moment of photons, photon moment is large in case of indirect band gap, but in case of direct band gap, the momentum of the photon is little. Next thing is that optical source. Optical, as you know that you already studied the block diagram of the optical fiber communication. So how the optical fiber communication is working. Optical source, optical fiber communication, which consisting of the major blocks like transmitter, the receiver, in between the optical fiber as the transmission medium. Optical transmitter converts the electrical input signal into the corresponding optical signal. Optical source is the major component in the optical transmitter. To convert electrical signal to the optical signal, this optical source is playing the vital role in the optical transmitter. So this popularly used optical transmitters. Which are the optical transmitters? Which are the optical sources? Popularly used optical transmitters are light emitting diodes, LED, and semiconductor laser diodes, LD. These two are the important optical sources. Next thing is that light emitting diode. A light emitting diode, LED, is a device which converts electrical energy into light energy. LEDs are preferred light sources for short distance optical fiber network because they are inexpensive. LEDs are inexpensive, they are robust in nature, and have a long life. Means long life of the LED is primarily due to its being a cold device. Means operating temperature being much lower than that of, say, an incandescent light. Today, when we're all using the LEDs in place of the incandescent lamp because of this the feature. Next, LED structure. So in LED structure, you are studying heterojunctions. What is an heterojunction? Dear students, heterojunction is an interface between the two adjoining single crystal semiconductor with different band gaps. Heterojunctions are of two types. One is isotype N2N or P2P, or anti isotype, that is P2N. We will see double heterojunction. What is double heterojunction? In order to achieve efficient confinement of emitted radiation, double heterojunctions are used in the LED structure. Heterojunction is a junction formed by dissimilar semiconductors. Double heterojunction DH is formed by two different semiconductors on each side of the active region, and the figure 3.1.1 so it shows double heterojunctions light emitter. So this is the diagram of an double heterojunctions emitter, light emitter. Double heterojunction in LED structure. The cross-hatched regions represent energy levels of the free charge. Recombination occurs only in the active indium gallium arsenide phosphide layer. The two materials have different band gap energies and different refractive indices. The changes in the band gap energies create the potential barrier for both holes and the electrons. The free charges can recombine only in narrow, well-defined active layer side, referred to the figure. A double heterojunction structure will confine both hole and electrons to a narrow active layer. Under forward bias, there will be a large number of carriers injected into the active region where they are efficiently confined. Carrier recombination occurs in small active region, so leading to an efficient device. Another advantage DH structure is that the active region has a higher refractive index than the material on either side. Hence, light emission occurs in the optical waveguide, which serves to narrow the output stream. Next thing is light source materials. Next topic is light source materials. The spontaneous emission due to carrier recombination is called electroluminescence. To encourage electroluminescence, it is necessary to select an appropriate semiconductor material. So that semiconductor materials which you can see in the next slide, the semiconductors depending on the energy band gap that can be categorized into direct band gap semiconductors and indirect band gap semiconductors. So this is the list of the semiconductors and their energy band gap and their recombination. Gallium arsenide, gallium indium arsenide, then silicon, germanium, gallium phosphide, and their energy band gaps in terms of electron volts, and the recombination is also given in the table. Thank you very much for seeing the video.